Hi, welcome to R2E, and this is Miramanoj Raman, and today in this video we will be solving problem number 3.9 of Daniel Kleppner and Kolenkow. So what this problem is titled is, this is problem number 3.9 and this is called tension in a rope. So what we have is we have a rope of uniform mass m and length L that is attached to a block of mass m, and the rope is pulled by a force F. So I need to find tension at a distance x from the end of the rope, and I'm supposed to neglect the gravity. Okay, so let's try to do this one. So, well, I have a box, yes, mass capital M, and with this I have attached a rope that is of mass some small m, and this is of length L. This is of small l, and there is a force capital F acting on it. Now, what am I supposed to calculate is the tension at a point X. So, what am I supposed to calculate is, okay, I'm supposed to calculate is tension at point X from this end of the rope. So, how am I going to do this? So, this problem is pretty simple, or by analogy, this problem is equivalent of having multiple, boxes being strung together by a rope, and you are pulling it from one end. Now, so what's happening out there is if you just cut the rope at this point and you try to observe it, you have your block, there's a force F acting here, and there is tension acting on the block. Now what's happening is that you have your force minus of tension, and that would be equal to the mass of the segment, let me write it as ms, times the acceleration. Now I assume the whole body is rigid, so what it means is that this whole system of this capital mass m and the small mass m, this will move together with the common acceleration. Now if I consider this as my whole system, so the acceleration of this whole system would be some a, and that a should also be the acceleration of this small piece of rope. So my a would be, for the whole system, F divided by capital M plus small m. All right, so let's give the equation number 1 and 2. Now the other thing I need to determine is ms. Now here's given that the rope is of uniform mass m, so what can I say is that the density is constant, that is m by L. So the mass ms would be just simply m by L times x. Demonstrates makes sense. Now, so let's put, okay, 2, 3. So let's put together 1, 2, and 3. So what we have is F minus T is equals to mx by L times F upon capital M plus small m. So this implies that tension is equals to F minus of small mx by L times F capital M plus small m. So this will be F times M plus small m times L minus of mx times F divided by capital M plus small m times F. So this will be equal to, well, F comes common, that is ml plus ml minus of x divided by m plus small m times L. Now, we essentially have the expression and it makes dimensionally sense that you have mass times length, and there you also have mass times length, and they just cancel out each other. But if you remember the statement out here, it says neglect the gravity. Now, why do we neglect the gravity? I mean, what's its implications of the implications of neglecting gravity? That's an exercise for you to think of, but let me give you a hint before that. If you include gravity, you also needs to, think about the torque. That is, I mean, if it's getting balanced and normal and rest of the things, also need to balance all sorts of things. And not to get into that details, we let the uh, we just neglect the gravity over. So we got the tension as a function of x, and it's some near linear function of it's a linear function. So as you go towards the length L, the tension seems to decrease. And yes, that's all you can get it from here. And one more thing out here is from this expression from right out here. So one can think of a limiting case that one can argue that can tension be greater than F? So is it possible? Well, actually, no, it's not possible for tension to be greater than F, because tension as such is not a real applied force, it's a response force. So why tension is generated in a string is that because you have a if you have a string out here, and suppose you have a block out here. So if you are pulling it, so the atoms inside it, so this if you think of it like a molecular chain. Now if you pull it from here, so the this molecule out here will tend to push it inwards, this whole system, so that it doesn't get separated in that sense. So there is a uh, because of the van der Waals forces, they stick together. So tension essentially rises because of the van der Waals forces. But on the same side, once you are pulling this system toward that side, toward this side, so the system on the left will also be pulled in that size, not only because of the force out there, but if you look at the local forces, because this force F is not getting applied at this point on this whole system. At this point, there is only tension, and that tension is just because of this van der Waals interaction between this molecule and this molecule. So this force will get transferred in this way um, to the rest of the molecules also. So what I'm trying to say is tension cannot be greater than this condition is not possible because of the fact that tension is a response. It's just like a it's just like a spring force. You can't have a spring to unnecessarily shrink if there's no force acting on it. So it can't happen that you are applying a force. You just try to you just if you have a spring like this, you just try to pull it in this side, and it just got shrunk just because the force because of the spring is higher than your applied force. Well, it doesn't happen in reality. It's like touching a switch and the spring automatically get compressed. Well, this is not something that happens in the real life. So this limiting case of tension being greater than force is not possible. And the other limiting case one would like to ask is what happens at x equals to 0. So at x equals to 0, the tension would be F times ml plus small ml divided by m plus small l. So that should be essentially equals to the force. So tension at this point is essentially force. And what about what happens to the tension when you reach at this point? So what's the tension at this point? So for that you need to put L equals to x. That would be here. So for x equals to L. I should use different color of pens, but from next on, from next time, I'll keep that in mind. So for x equals to L, the tension would be equal to F M L divided by capital F plus small m times L. So again, this is mf by capital M plus small m. So this is essentially the force required so that this body moves with the same acceleration as that of the whole body. So we discussed the limiting cases, that what happens at x equals to 0, what is the tension at x equals to 0, what is the tension at x equals to L, and can it be possible that tension be greater than force? So the answer was no, tension cannot be greater than force, because tension is a response force to the applied force. You have control over your applied force, but not over the tension. Tension arises because of the van der Waals interactions in the molecules. Thank you for watching the video.